So the title of my talk is Quantum Gravity from the Lattice. So let's begin with the classical theory of gravity. So it was introduced in 1915 by Einstein. So far, it is the most accurate theory of gravity. That we know, it is a classical field theory. It contains the field equations given by this. Is there a stick or something? There is. Let's see what organize. Stick-wise. My strategy is to use the cursor. The cursor. Okay, all right. Okay, so then, yeah. That will be great. Thank you. Yeah. Yeah. Oh, it's working. Thank you. Okay, so let's begin with the classical theory of gravity. It was introduced by Einstein in 1915. So this is the most accurate theory of gravity that we know so far. So they're having so many observation tests, and GR was successful. All of this. So it is a classical field theory. By the way, this was about the first observational test of GR. It happened in 1990. So there is one prediction from GR where the bending of light by the presence of a massive object. So it is the sun. So they were able to capture the bending angle, and it was very, very close to what was predicted by the GR. Okay, so it is a classical field theory. So it contains these field equations given by this. So on both sides, there are different things. On the left-hand side, we have the curvature of spacetime. This is the metric tensor. This is the curvature tensor. It tells matter how to move in a curved spacetime. And on the right-hand side, we have the matter of energy. This is the energy momentum tensor. And the matter is telling spacetime how to curve. Okay, so they are equal back and forth. Okay, now coming to classical theory of electrodynamics. So we have Maxwell's equations. They describe the theory of electricity. In other words, the theory of light and matter. So we have the Maxwell's equations given by this, homogeneous and inhomogeneous, all of them. We can introduce this in the relativistic framework. and we can come up with the relativistic form of Maxwell's equations. So let's introduce the scalar and vector potentials. So you already know this from your course of electromagnetism. So we can express the electric and magnetic fields. These are the physical fields in terms of the scalar and vector potentials in this way. Now let's combine the scalar and vector potentials to get a four-dimensional vector, which is denoted by this. And from this vector, we can construct a tensor, which is the electromagnetic tensor, which is given by this. It is an antisymmetric tensor. So now this tensor encodes electric and magnetic fields in this way. So components of this electromagnetic tensor, they contain electric and magnetic fields. Now, invoking relativity, we can combine these four equations into two equations. Okay, so we can take the homogeneous equations and combine to form this. So this symbol means completely antisymmetric in indices. And we can combine these two equations and get this equation. Okay, so we have this beautiful form of relativistic Maxwell's equations. So here, the field A mu represents the electromagnetic field. We can quantize this field, and what we get is the photon, which is the quantum of electromagnetic radiation. So it is a massless spin one particle, and we can write out the Lagrangian for the photon field, which is given by this. So take the electromagnetic tensor, then contract the indices, and we get this. Then integrate over the space-time. So integral d4x means integrate over the free volume and integrate over time. What we get is the action, which is a known. So the action is given by this. Now, coming to quantum version of electrodynamics. So we can have quantum electrodynamics. It is the quantum theory of light and matter. So light and matter, they interact schematically like this. So we have one electron going in space-time, and it emits a photon, and there is a recoil and the radiation symbol, a photon symbol. Okay? And there is an interaction vertex, which has a certain strength, which is given by the electric charge. So the Lagrangian for QED is given by this. So we have the term that containing the photon, and there is a term containing the fermions, and there is a term containing the interaction between the fermions and the photon. Okay. So this quantum electrodynamics, it is a renormalizable theory. So that means this theory has no infinities. Okay. So just fix the mass and charge. So we have the charge here, we have the mass here, and do some experiments, fix mass and charge, and put that into the theory, and it removes the infinities. Okay. So this theory is renormalizable, and this is what is the most precise theory in physics. Okay. So what the theoretical predictions, they agree extremely well with experiments. Well, there's a big question on the methods, various methods. Okay. Okay, now coming to quantizing GR. So one might ask, we are able to quantize electromagnetism. So how about quantizing GR? Is it that straightforward? So answer is no. So the question is how to describe gravity according to the principles of quantum mechanics. So the problem is general relativity is not perturbatively renormalized. Okay. So the theory contains infinitely many independent parameters. So that means we need to do infinite number of experiments to fix these parameters. Okay? Like mass, in electromagnetism, we have mass and charge. So in GR, there will be additional terms coming added to the Lagrangian. Okay? And infinite number of such terms are there. And we have to do infinite number of experiments to fix the partitions. Okay? So in that way, GR is not renormalizable in that question. Okay, now coming to string theory. So string theory is a generalization of quantum field theory. So here, instead of point particles, we have string-like objects. They propagate in a fixed space-time diagram. Okay, so they are basically strings, So if you look at the point particles, so there is a particle 1, particle 2, these are point-like particles, they come, they move in space-time, and at this point they interact, and particle 3 is coming out. So this is a tricky situation. All of a sudden, two particles are changing into one single particle. Okay? So this is, it's not so gentle, the situation. Now, if you replace this interaction with strings, okay, there's a string 1, there's a string 2, moving in space-time, and the strings are joining to form a single string. So there is nothing happening all of a sudden. Okay? So it's a more gentle type of process. Okay, now the spectrum of strings, it contains massless spin-2 particle, okay, which is nothing but the graviton. So graviton appears as vibration mode of closed strings. So here is a schematic picture. So gravity is unavoidable in string theory, okay, which is amazing. So string theory was originally started as the theory of elementary particles to explain the strong interaction. Okay? So when people started formulating this, they discovered that it contains spin-2 particle, which is the graviton. So gravity naturally emerges from string theory. Okay? So in that way, it is a quantum theory of gravity, which is a good thing. Now, string spectrum also contains massive particles as vibration modes with charge and spin. So the goal of string theories is to get the standard model of particle physics from string theory. Okay? So string theory inherently contains particles with mass and charge, and it also contains massless particles with spin 2. Okay? So string theory is a very compelling candidate for a unifying the four fundamental forces.
Can I ask a question? Thanks to follow the path of the tell me that I'm always trying about this. So you have got something that's a spin object, but actually highlighted it's in a fixed space time background. So how do I go from that to the classical nature of gravity?
Yes. So the presence of these gravitons, these closed strings, it will change the background. So the fixed background becomes a dynamical background. So that is how we go around this. Okay? So soon I will come to how the background changes. All right. So the goal is to get the standard model particles from string theory, but it's not an easy goal. Okay, because string theory lives in very high energies, and standard model is an effective field theory, which is a low energy field. So we need to get there from very high energies. And there are several ways to get there, and we are still struggling to find what is the correct way to get here to the low energy effective field. Okay, so string theory in general, it contains objects called D branes. Okay. So these are generalizations of membranes. So these D-brane objects, they contain energy. So it's like a rubber band, like a membrane. It contains energy per unit area or unit volume. It contains certain types of charge. So here is a schematic sketch of various types of branes. So there's a zero brane, which is like a particle. Then one brane, which is a string. It has a tension and everything. There is a patch of a two brane. It's like a membrane. Then there is a three brane, which is like a piece of the volume, three-dimensional volume. Now we can close these objects. So we get a closed string. We can get a closed two brane, but we don't know how to imagine this, but it can happen. Okay. So when we say string theory, it contains all these objects within the theory, not just strings. Yeah, which is like a pointer particle. But there are dualities. Okay, it's not just a point particle sitting there. Okay, it can convert into a string. That is the end of a string. So a string can attach to this point. Okay, a string can attach to this membrane as well. Okay, and this membrane can attach to this thing, this object. No, they are all postulated. And you need to impose certain boundary conditions or these things. Yeah? So it's like a mix of all these things, and one can form break into other entities. So a brain and an anti-brain can come together and collapse and form straight and solid zero brains. All those things. Okay. All right. Now there exist several versions of string theory. So people discovered various types of string theories at various times, and later they realized that they all form part of one single theory, which is called the M theory. So this M theory can be reduced to these various string theories by taking various limits and applying various dualities. Okay, now coming to GR and black holes. So black holes can provide a window into quantum gravity. Okay, so the prediction from GR is sufficiently compact mass can deform space-time to form a black hole. So black hole is a region of space-time where gravity is so strong that no particle can escape. Okay? So the simplest black hole is something called Schwarzschild black hole. It's like a spherically symmetric black hole. So before moving on to the black hole geometry, let's introduce the concept of metric. So a metric defines distance between 2 points. Okay, so in Cartesian planar coordinates, take 2 points in a plane, x1, y1, and x2, y2, and there is a distance between these 2 points. And the question is, how do we define this distance? How do we measure that length between these two? And it is given by the metric. Okay, so here the metric is this. It's the line element, another way to say this, which is given by this. And if you go to 4-dimensional space-time, 3 space and 1 time, the metric is given by this, and this space is called the Minkowski space. Okay? And here is the metric. And instead of Cartesian coordinates, we can go to spherical coordinates, where the metric, the same metric, it takes this form. So here, d omega 2 square, it is the metric on a 2-sphere of unit radius. Okay? So whenever we encounter problems with spherical symmetry, we can use this metric. Okay? So depending on the problem. Now coming to the metric of the simple spherically symmetric black hole, which is called the Schwarzschild black hole, in 4 dimensions, 4 space-time dimensions, it has this particular metric. Okay, and here we can see certain interesting properties. One is this particular length scale. When this is equal, this length scale equal to this, what we get is a 0 here, and we get 1 over 0. Okay, so the metric shows some funny behavior. So this length scale has a name. It is called the Schwarzschild radius or the horizon radius. Okay, and which is given by this. It's proportional to the mass of the black hole and the Newton's laws. Okay. So here is a schematic sketch of the Schwarzschild black hole. It's a spherically symmetric black hole. It has a horizon with radius given by this, and there is a singularity at the center.
That's singularity. That's not this radius average.
That is the radius average.
Oh,
from the center to here.
but sorry, what I have to ask is this. You see, I mean, so this the radian is from infinite to negative, and are right?
No, that is not the way to think about it.
So I mean, there's an infinite. This expression blows up.
This thing blows up. Yeah, yeah.
No, my question is that just like.
No, this is yeah. It becomes undefined. Okay.
But it's
so that yeah, exactly. Yeah. You can use a different coordinate system, and you will see that at the horizon nothing funny is happening. It's smooth. And here is another way to look at this. So here again we can see that the space-time is curved. Okay, so there is a curvature. Singularity here and the Schwarzschild radius here. Now, if we move far away from this black hole, what happens to the space-time is it becomes the flat metric, okay, the Minkowski space. So in other words, this black hole is embedded in mid-velocity space. Okay? So there's a flat asymptotic, there's a flat mid-velocity space, and the black hole is embedded in that. As we approach the black hole, the space-time changes. There is a curvature. Okay, now we can generalize this metric to d space-time dimensions. So where the Schwarzschild black hole, the metric looks like this. Okay? So the power changes. That is the main thing, and this unit sphere that also changes. Now, coming to classical black hole, the black holes described by GR, they are at 0 temperature. Okay? So they don't emit any radiation. So for a Schwarzschild black hole, everything is fixed by its mass. In 1975, Hawking, he used GR and the QFT he tried to combine the two and did some calculations, and he got this result. So black holes are not black; they actually emit radiation, and the temperature is given by this. It's like a black body. Temperature is given by this. It's related to the mass of the black hole and the Newton's constant. So black holes are thermodynamic entities. Okay? So they have entropy, internal energy, all these things. So here is a schematic diagram of how Hawking radiation happens. So in vacuum, we can have particle and a particle pair. This is called a virtual pair because it's not physical. You cannot measure it. But they always do this dance of creating and disappearing. Okay? So when they do that dance near the horizon, one of them goes into the black hole. So then they cannot be virtual anymore. Okay? So this thing escapes with taking some energy from the black hole. Okay? So that is coming out as the Hawking radiation. Okay, now let's look at another kind of space. So we looked at the flat Euclidean, so the mid-velocity space. We looked okay. So this space, denoted by this, it is a surface embedded in a flat space given by this. Okay. So the metric of ADS n+1 is given by this. It has two time-like coordinates and n space-like coordinates. Okay, and this object, it obeys this constraint. Okay, so if we embed this space within a flat space, it has to obey this constraint, and there is a surface which is obeying this constraint. And this capital R is called the radius of the alien space. Okay, it is a homogeneous space. That means no point is special within the space. Any point can be mapped to any other point through a symmetry, which is called isometry. Okay, these are transformations. It takes one chunk from another chunk within the space, but it looks the same. So here are some examples. This is ADS2 space. It looks like a hyperboloid embedded in three-dimensional space. And here is another depiction of ADS space. Although it looks finite, it is actually an infinite volume space. Okay? So if you move from the center, if you measure the distance from the center to the boundary, what we see is it's an infinite distance. Okay? And here is the time direction. So this is called the point current patch. There are different ways of representing space. Okay, now ADS space also supports black holes. Take ADS space, we can embed a black hole in this ADS space. Okay? So the geometry of the space is deformed by the presence of black hole. As we move away from the black hole, the space-time approaches the original ADS space. Similar to what we saw earlier, as we move away from the Schwarzschild black hole, the space-time becomes a mid-velocity space, asymptotically flat. So in finite-dimensional ADS space, the Schwarzschild black hole, it has this metric. Okay, so we can see there are two ratios. There is a length scale capital R. There is a length scale R0. So here R0 is related to the mass of the black hole, and capital R is fixed by the ADS radius. This black hole has a Schwarzschild radius, which is given by this. This black hole also has a temperature, which is given by this. This is the Hawking temperature of ADS. Okay. So that means this is also a quantum black hole. It can emit radiation. Now, if you look at this metric and take this particular limit, R becomes much larger than this R naught. So it becomes a metric of ADS space with this ADS radius. Okay. Capital R is fixed. So it takes this particular form. This is the metric of ADS space. Now, if you take from this metric, if you take the ADS radius to infinity, what we get is the metric of Schwarzschild blank in enclosed. So there are these connections. You can take various limits. Okay, now again, from this metric, for a fixed large R, take this limit, R square over R square, much greater than 1. This metric becomes something like this. Okay, this is a familiar metric. We saw this earlier. So this tells us that there is a boundary which is given by this R cross S3, and with the sphere S3 having this radius R of the ADS space. Okay, so there's a boundary of this ADS space. So that will be useful later. Okay, now coming to, so I'm slowly connecting all the ingredients. So coming to the holographic principle. So we all know what a hologram is. So a hologram reconstructs a three-dimensional image from a two-dimensional surface. Okay? So holographic principle, it tells us that physics of the d+1 dimensional bulk is encoded in a dual d-dimensional theory. Okay, so there is a three-dimensional bulk which has some physics. That physics is encoded on this two-dimensional surface. Okay, so that is what holographic principle is telling us in general. So it doesn't have to be 3 or 2, it can be d+1. Okay, so examples. So we have a bulk theory, which is a two-dimensional theory, which is like this or something. And we have the edge. This edge is a boundary, which is one dimension. Okay. So the holographic principle tells us that the physics, whatever is happening here, it is encoded on this edge. And similar to higher dimension, bulk is three-dimensional, boundary is two-dimensional, like a cylinder. Okay, holographic principle, it has several names. We have several names in the literature. Other names are gauge gravity duality. So the bulk theory is the gravitational theory. Boundary theory is the gauge theory, or a quantum field theory, which has no gravity. Okay? There is no gravity here, but the theory inside, it is a gravitation. Okay? So what do we mean by duality? It tells us that same physics is described by two different physicists. They appear different, but they describe the same physics. Another name is ADS CFT correspondence. So the bulk theory is living in ADS space. Okay? So this is why I introduced the space-time. And boundary theory, it is a conformal field theory, okay? Which is a special type of quantum, which is scaled in. So this is another name. And there is another name which is weak, strong duality. So bulk theory, it can be a weakly interacting theory, and the boundary theory can be strongly interacting. Okay, so now there is a requirement for holograms, which is symmetries must match on both sides. Okay, the bulk theory, it has some symmetries, and the boundary theory, it has some symmetries, and the symmetries must match. Okay. This is a statement independent question. Okay? That's nothing to do with question. So a real such.
Saying that any involved theory, like any quantity theory involved, it corresponds to another theory somehow.
No, not any.
But there are other things than string theory that also put in the block and keeping like. I mean, I'm just trying to understand that.
Yeah, so the idea is there are degrees of freedom living in the bulk, degrees of freedom living on the boundary, then there has to be a matching. So on the boundary, suppose you want to encode all the degrees of freedom on the boundary, it shouldn't be infinite. In the bulk, it shouldn't be infinite. It should be finite in a certain way, so that you can map. So that is one requirement. And area space has that beautiful property that you can actually map. It's not infinite. Okay? Flat Minkowski space, it does not have that property. But there may be ways to map it. Okay, so in a particular realization, the bulk theory is ADS spacetime, okay, ADS phi, and on top of that, there is a phi figure, okay, which will be useful from the boundary theory. And on the boundary theory, spacetime is Minkowski space. So bulk theory is the low energy limit of string theory. And on the boundary theory, we have a specific type of quantum field theory, which is a supersymmetric dynamics theory. Bulk theory contains a black hole. That means the space-time is curved. There are closed strings moving around in the bulk theory. Okay? And this is coming from D3 branes in this particular setup. And the boundary theory, which is a quantum field theory, and this is in a confined phase, so a deconfined phase. Okay? So there is a confined phase and a deconfined phase. This is separating how the degrees of freedom behave. Okay? So the free energy of the theory in a deconfined phase, it goes like n squared, where n is number of degrees of freedom, and in confined phase, it goes like 1 in power 0. Okay? Now, these black holes in the bulk theory, it has n units of electric charge. I'll put electric in quotes, 7 charge. And in the boundary theory, it has a gauge symmetry, and it is controlled by this particular grid. Okay? And n appears here because there are n units of electric charge, or n number of electrons. And the bulk theory has a temperature. It contains a quantum black hole with a Hawking temperature T. And the boundary theory, it is a finite temperature theory with the same temperature. Okay? It's like there's one realization. There are many such realizations. So in this setup, the boundary theory is a conformal field theory. So in 4 dimensions, there are the set of conformal symmetries. They are generated by 15 operators. And that includes rotation, Solomon's use. You add them up, you get 15 of them. So conformal symmetries, they act on the field theory as a set of field transformations. So you can apply, say, a rotation in the field, a boost on the field. So these symmetries, they must appear on the other side. The symmetries must match. So in the bulk theory, this theory lives in this particular space, ADS phi cross S5, and this space has 7 symmetries. Okay? You can map a patch to another patch, and it looks the same. Okay? So those symmetries are called isometries in GR, and it is generated by 15 operators. Okay? Yeah. So the 15 operators on both sides, in this particular case, they satisfy the same algebra. Okay? Yeah, so that is this realization. Now, coming to quantum gravity, so holographic principle, it dramatically shifted our understanding of the relationship between the theory of gravity and the quantum interacting particles, okay? Quantum field theory. So this is telling us that quantum gravity in higher dimension spaces can be precisely captured by the quantum field theory that lives in a lower dimension space, okay, which is a profound statement. Okay, now let's look at some specific cases. So this is related to my research. So consider a variation of the holographic principle. Let's look at this particular space. ADS P+2 in the bulk, and QFTs in P+1 dimensions, okay, on the boundary, 1 dimension plus. So the gravitational theory is a low energy string theory, which is called supergravity. That is Einstein's GR plus some other things, okay, like Fermi fields, etc. So this bulk theory contains black DP branes. That means you take a bunch of deep rings and bring them together. Since they have tension, they have mass, they can collapse to form a black hole. Okay, they can go inside the price. So they become a black. So it contains n units of electric charge, and the theory is at finite temperature T. So on the boundary theory, we have a supersymmetric non-abelian theory, which is the Yang-Mills theory, in p+1 dimensions. Okay, and this theory has gauge symmetry controlled by this SUN group. This theory is strongly coupled. This theory is weakly coupled, and it's a finite temperature, same temperature. Okay, so let's look at this simplest case, which is P equal to 0. So what we have is ADS2 in the bulk, and QFT 0 plus 1 on the boundary. QFT 0 plus 1 is nothing but a quantum mechanics. Okay? There's only time, there is no space. It's a quantum mechanics theory. So we have a theory of zero brains, these zero brains, with n units of charge at temperature T. So there is a black hole in this phase. And the boundary theory is a quantum mechanics with this particular gauge group. It's strongly coupled, and it's at temperature. So the metric is given by this, the area space. There is a black hole. The temperature of the black hole is given by this. It can be computed in string theory. So we also get expressions for entropy, internal energy. So in 1998, a string theory computation, it produced the internal energy of this black hole. Okay? So the internal energy of the black hole, it is some coefficient, which is given by this, times temperature to this specific power. Okay? So it was derived in this paper. Okay? Now the question is, can we reproduce the thermodynamics of this black hole in gauge theory? Okay? The dual theory, which is the quantum mechanics living on the boundary of space. And this theory contains no gravity. This theory, the bulk, contains a black hole. It contains gravity and strings, all those things. So can we get this expression with A naught 7.41 and T naught from the base? So that is the question. On top of this, we can add quantum gravity corrections coming from the black hole, which goes like this. A specific coefficient and the T power this number. And this was computed in 2013 in string theory. So they calculated the foregravity of scattering. Got this. And there can be string oscillator corrections. They are coming from this. They can add these contributions to the internal energy black hole. The coefficients A and B, they are not yet known analytically in string theory, because it's not easy to compute. It's a long function. So we can have a series of corrections from string theory that it goes like this. There are lots of coefficients. So the question is, can we reproduce this in the boundary? Okay. Now, going to the theory living on the boundary, it is a strongly coupled quantum theory. That particular theory is known as the BFSS matrix model. It is a matrix quantum mechanics with a large number of fields. So this is the action of that quantum mechanics. So these are like a bunch of oscillators, okay? And they are interacting. There are bosonic oscillators, fermionic oscillators, and they are interacting. That is what this action represents. And these are all matrices. So here lambda is the coupling within the theory, and we can take this Yang-Mills coupling square times the size of the matrix, which is this, to get coupling called the truth coupling. This is the relevant coupling. The theory contains 9 scalars, and there is an SO9 symmetry, and SO9 symmetry is the symmetry of the sphere S8. Okay? So in the bulk theory, it is ADS2 cross S8. Okay? There's only an S8 there. And that information of that S8 is captured in this SO9 symmetry of this 9 series. Yeah, and there is a one gauge field, and again 16 fermions. These are all requirements coming from supersymmetry, right? Because they all have a 15 number of fermions and electrons. There are gamma matrices, which gives some structure for this. All fields transform into adjoint representation of the gauge field SUN. And the field theory is at temperature T, which is the inverse of this circumference. It's a finite temperature. Okay, now so from gauge theory side, we have a strongly coupled theory. So we cannot do perturbation because the coupling is order 1 or higher. So we need to resort to non-perturbative methods. So what we do is we discretize the theory on a lattice, on a space-time lattice, and write computer codes and run the codes and with the physics.
It's based on just have time.
Yeah. So you displace time. In other variations, you displace it. Okay, so we can use lattice, space-time lattice as a regulator. One of it has infinities. And the lattice is a first principles approach, where the infinities are tamed by the presence of this finite lattice space. So place the degrees of freedom of the field theory on the sides and lengths of the lattice. So this is a one-dimensional lattice. This is the lattice we will be using for the quantum mechanics. There's a lattice spacing, which is an ultraviolet cutoff, and there is size of the lattice, which is the infrared theory. So we can go to higher dimensions. We can build higher dimensional lattices. So the origin of lattice field theory. So in 1974, Ken Wilson, he suggested that we can regularize the theory of strong interaction, quantum chromodynamics, on a space-time lattice. And we can try to extract the nature of the strong force, whether it's confining or not. And he was able to show that QCD was confined in 1974 from lattice calculations. So this is the Lagrangian of quantum chromodynamics, the theory of strong interactions. So we saw this structure before electromagnetism. So we added one more index, which represents the color indices, new charges, color charges. And this is the fermionic part. These are quarks, and they interact via with the gauge bosons through this covariant derivative, and the structure is given by this. So basically, we have more number of things, okay? And they have to obviously be structure, set a relationship. So place the quarks, the fermions, on lattice sides, and gauge fields, set the gauge fields on lattice lengths. Now, lattice QCD, it is a very successful machine. Okay? It has produced lots of results, and it is giving input to particle providers like LHC. It is making predictions, all kinds of things. So it's a very mature field. So we can compute masses of particles, form factors, matrix elements, scattering, and decay constants of elementary particles. Many kinds of things we can do using lattice QCD. So the approach is based on path integral quantum field theory. So what we do is we take the action of the theory, exponentiate it, and integrate over all field configurations. What we get, so this integral is an infinite dimensional integral. Okay? So we need to use, if we introduce a lattice, we can bring this down to a finite dimension. Okay? Because lattice can accommodate only finite number of degrees of freedom, okay? So that we can handle it. Then we can compute the expectation value of an observable using path integral formalism like this. But on the lattice, we replace this with a summation. Okay? Integration with summation on the lattice. So to increase the efficiency of the summation, what we do is we give preference to terms in this exponential, and where this exponential is contributing the most. And that happens when these actions minimize, minimum action configurations. So we don't simply sum over all fields, all field configurations, we take only the important ones. where the action is minimized, and that is called the impermanent sample. Okay.
How do you find which ones are
There is a way to find that. I may go into that, but there is a specific method to directly point to that direction. So that method, that algorithm avoids, it gives preference to the places where action is made.
So we are finding saddle points.
Yeah. Okay, so I already explained this important sampling. Then save the field configurations. You run the code, run the program. It eventually finds these minimum configurations, and most of the time it spends there. Okay? So you can pull out those field configurations and save them, and you can use that field configurations to construct the observables. Okay, algorithms. This is actually your question, but I am going to go into that. Already done late. So there are algorithms. Okay, how do we put a quantum field theory on a grid or space-time? So there are specific algorithms. Okay, so that we can extract the physics. So I'm going to the algorithms. Okay, now coming back to matrix models. So let's come back to the BFSS matrix model. So this is the original paper where this matrix model was introduced. So this model is obtained by dimensionally reducing a 10-dimensional theory or a 4-dimensional theory with n equal to 4 supersymmetry, or a 10-dimensional theory with n equal to 1 supersymmetry, down to 1 time direction. Okay? So the proposal was this matrix model is exactly equivalent to N theory. Okay? It contains all the information about the string. That was a proposal. So the action of the theory, we looked at this earlier. It contains fermions and bosons. So what we do is we can put this action on a lattice, a 1-dimensional lattice. Okay? So schematically, this is the lattice. There are lattice sides. So you place, say, the scalar fields on the lattice sides, then the fermions on the lattice sides, then there is a gauge field which is sitting here. It lives on the link connecting the two sides. Okay, so carefully place them on the side, on the lattice side, so that we can extract this action from this, which will give us the number. Then do the simulations. So back in the days, in 2008, so these two people, they did a Lattice Monte Carlo study of this model, and they got these data points. Okay, they are coming from numerical computation. So what is given by supergravity or low energy string theory, this equation, which is this. Okay, so the Monte Carlo results are kind of agreeing with the supergravity. Yeah.
The efficiency is supposed to be anything in the larger limit.
Yeah, larger. So this was a crude lattice simulation. Back in the days, they didn't have that much computing power. Now there is a more modern result, which is coming from 2016 by this collaboration led by Masneri and others. So where they did a careful study of this model. Okay? They used a supercomputer to produce these data points. Okay? These are coming from Monte Carlo, the lattice computation. And they are fitting this to various models. So this is the prediction from low energy string theory, okay? The internal energy of the black hole. And this is what is coming from the strongly coupled field theory, which is living on the boundary. So there are deviations. So the deviations are coming from these higher connections. Okay? So the leading order prediction is just this term. Okay? But the prediction also contains these terms. And these terms will bring these points to this curve. So then they try to fit the data, the numerical data. And what they get is if you keep everything free, the coefficients are coming out like this. So what we want is 7.41, but they are getting is 7.4 plus or minus 7. So within errors, it is matched. So this is a theory that contains no gravity in it. It's living on the boundary. Still, it captures information about the bulk theory, the black hole, of areas 2 processing.
And what was their end in this?
They started with the minimum 16, and they went up to, I don't know, 64 or something.
But that's not very much.
For large n, anything to 3, 1 by 3 is, so 1 by 64 is, what is it? 64 is large n.
Why did
You will, I mean, in simulations, you will see large n effects by n equal to 4 or 5. Then it doesn't matter as you increase n equal to 10, 20, it doesn't change that much. So 64 is like we're pushing it too far. But still they did it. They had access to the computer at Lawrence Livermore Land in California. So they just pushed it. So they also computed other coefficients. Okay, these are unknown coefficients. So they computed those. B naught is known -5.77. What they are getting is -5.8. So that is very interesting mention. Then another computation from Japan, they did again simulations, and this is the supergravity prediction, and this is the lattice result. Again, this lattice knows about the quantum gravity coefficients and the string oscillator. So that is why it's deviating a bit. Okay, now moving on to another matrix model, which is called the BMN matrix model, which is a deformation of the original BFSS matrix model. So here what happens is we have a black hole in the bulk, and you introduce an external field onto the system. Okay? So that deforms the MTF line. So this is a particular deformation of the BFSS. Again, this has a gravity dual, and people have studied the gravity dual. So let me go a little faster. Time is 2:10. So there was a prediction from string theory for this model in 2015. That prediction was in the strong coupling limit, the ratio, the temperature of the theory with respect to this deformation parameter, it approaches this value. Okay, so that was a prediction from string theory. And in the field theory, what it means is it separates two phases within the quantum mechanics. Okay? So there is a deconfined phase and there is a confined phase where the free energy jumps. Okay? There's a phase transition happening. And basically, they computed the boundary of the phase transition at strong coupling. Okay? This is coming from string theory. Now, the question is, can we reproduce this the gauge theory, the boundary? Okay, that would be another validation of this holographic. So here we can do perturbation theory, decoupling, and people have done that, and they get this result, which is here. Okay? And this is the strong coupling result. So it increases and it saturates to this value. Now again, we can do lattice computation similar to what we did earlier for the BFSS model. We can compute this observable, which is called the Polyakov loop, which is the holonomy, the gauge field going around the lattice. Okay? It is a non-local observable. We can measure this, we can compute its value, and it is tied to, it will give us where this transition is happening. So we did that. These are our lattice configurations. These are our preliminary results. So again, we are getting the data from lattice computations, and we are fitting to this function. So we want to find where the free energy is jumping. So here, it's at the inflection point, it is jumping, and here at the peak, it is jumping. So as we increase the n, the size of the matrix, it becomes a sharper transition. Yeah.
Why did you fit it to the sequence function?
You don't have to. We can fit it to any other function that shows us the inflection.
Just once a while.
Yeah. So what you need is it changes its slope. Okay, the slope is changing something. You want to get that where it is. You can fit it to some other thing. Okay, all right. So this is our preliminary result. which is so the result from gravity is shown here. And that is predicting that the phase transition should happen at this value at strong coupling. Okay. So these are our lattice computation results. So slowly it is approaching. So simulations are still going on, and it's already matching with the weak coupling result. And this is our next to next leading on perturbation theory result. As you can see, perturbation theory breaks down as the coupling sequence. It is applicable maybe applicable. This is a non-perturbation direction, strong perturbation. Yeah, in BM. The result from holography is this from the graph. Okay, so I guess that's all. So we did I showed you validations of two different models, which reproduces the result from the string theory or the gravitation. So black holes provide a window in the quantum gravity. So certain spacetimes with black holes, they have QFT at the boundary. Not all spacetimes, certain spacetimes. Boundary theory acts like a hologram that captures physics of the boundary. Holographic principle was tested in lower dimensional theories. In this talk, there are other cases where we have tested the models as well. So lattice calculations of strongly interacting quantum theory, it gives accurate checks for predictions, which is amazing. A theory that does not contain gravity, it shows, what is happening in the world. It captures the essence, which is something mysterious. Okay, so that's all.
Questions?